Light defines speed. It is the universe's absolute limit. Nothing can move faster. For over a century, we have known this fundamental truth. Light in a vacuum travels at exactly 299,792,458 meters per second. This speed is carved into the very fabric of space-time itself. But what if, just for a moment, we could stop it? What would that mean? What would light become when the fastest thing in the universe suddenly stands still? This might sound like science fiction, like something that violates the deepest laws of physics. After all, if light stops, does time stop too? Does reality itself break down? These questions have puzzled scientists for decades. But here is the remarkable truth. It is not speculation anymore. In laboratories around the world, physicists have actually done it. They have taken beams of light, pulses of pure energy racing at cosmic speeds, and brought them to a complete halt. Not slowed down, not deflected, stopped. The light does not disappear. It does not get destroyed. It simply waits, frozen in place, like a photograph of motion itself. And when scientists choose to release it, the light continues on its journey as if nothing happened, carrying the same information, the same energy, the same quantum properties it had before. This is not magic. This is quantum physics at its most mind-bending. To understand how light can stop, we must first journey into the deepest nature of light itself. We must explore what light really is, beyond our everyday experience of sunshine and shadows. Only then can we grasp how something so fundamental to our universe can be paused, stored, and released like a cosmic remote control. The story begins with a simple question that opens up extraordinary possibilities. Can light be frozen in place? To understand how light can be frozen in place, we need to dive deep into one of physics' most beautiful and enduring mysteries. What exactly is light? This question has puzzled humanity for thousands of years. From ancient Greek philosophers, who debated whether vision worked by rays shooting from our eyes, to modern quantum physicists who have discovered truths about light that seem to defy common sense and challenge our basic understanding of reality itself. For centuries, the greatest scientific minds debated this fundamental question with passionate intensity and rigorous experimentation. Is light made of particles, like tiny invisible bullets shooting through space at incredible speeds? Or is it a wave, like ripples spreading gracefully across the surface of a still pond, carrying energy without carrying matter? The debate raged for generations, with brilliant scientists on both sides presenting compelling evidence for their theories. Isaac Newton, one of history's greatest physicists, championed the particle theory. He argued that light must be made of tiny corpuscles that travel in straight lines and can be reflected or refracted when they hit different materials. His mathematical genius and the success of his other theories gave great weight to this idea, and for decades, the particle theory dominated scientific thinking about the nature of light. But then came experiments that seemed to prove Newton wrong. Thomas Young's famous double-slit experiment in 1804 showed that light could interfere with itself, creating patterns of bright and dark bands that could only be explained if light behaved like a wave. When light passed through two parallel slits, it created an interference pattern on a screen behind them, exactly like water waves would do under the same conditions. The wave theory gained more support when scientists discovered that light was part of the electromagnetic spectrum, related to radio waves, X-rays, and gamma rays. James Clerk Maxwell's equations in the 1860s described light as oscillating electric and magnetic fields propagating through space, providing a mathematical foundation for the wave theory that seemed unshakable. The answer, discovered through decades of brilliant experiments and theoretical breakthroughs in the early 20th century, turned out to be far stranger than anyone had imagined. Light is both particle and wave. existing in a state that defies our everyday intuition about how reality works. This discovery helped birth the field of quantum mechanics and forever changed our understanding of the universe. Light exists in what physicists call quantum duality, one of the most mind-bending concepts in all of science. It behaves as both a particle and a wave simultaneously, switching between these identities depending on how we choose to observe it and what questions we choose to ask of it. This is not a limitation of our measuring instruments or a sign that we do not understand light well enough. It is a fundamental property of reality at the quantum level. When we think of light as particles, we call them photons. These are packets of pure energy with no mass, no electric charge, no physical substance at all, in the traditional sense. Just momentum and information racing through the cosmos at the ultimate speed limit. Photons are quantum objects, meaning they follow the strange rules of quantum mechanics that govern the behavior of the smallest components of our universe. Each photon carries a specific amount of energy that depends on its frequency. High-frequency photons like gamma rays carry enormous amounts of energy, enough to damage living tissue and break apart atomic nuclei. Low-frequency photons like radio waves carry tiny amounts of energy, so small that billions of them can pass through your body every second without you noticing. Visible light photons fall somewhere in between, carrying just the right amount of energy to trigger chemical reactions in your eyes and allow you to see the world around you. Photons are the fundamental units that carry the electromagnetic force, one of the four basic forces that govern everything in our universe. The other three forces are gravity, which holds planets in orbit around stars, the strong nuclear force, which holds the protons and neutrons together in atomic nuclei, and the weak nuclear force, which governs certain types of radioactive decay. The electromagnetic force carried by photons is responsible for virtually everything you experience in daily life, from the chemical bonds that hold your body together to the electrical signals in your brain that allow you to think. Photons are messengers of energy and information, carrying power from stars to planets, from light bulbs to our eyes, from radio transmitters to our phones, from the screen you might be watching this onto your retina. Every time you see anything, photons are streaming into your eyes at incredible rates, carrying information about the color, brightness, and position of objects in your environment. Your eyes detect these photons and convert their energy into electrical signals that your brain interprets as vision. But light is also an electromagnetic wave, and understanding this wave nature is absolutely crucial to grasping how it can be manipulated and eventually stopped. Picture two invisible fields, electric and magnetic, oscillating perpendicular to each other as they race through space in perfect harmony. These fields are not made of matter in any conventional sense. They are disturbances in the fabric of space itself, regions where charged particles would feel forces if they were present. The electric field creates the magnetic field, and the magnetic field creates the electric field in an endless dance of mutual creation that has been going on since the birth of the universe 14 billion years ago. This self-sustaining oscillation allows electromagnetic waves to travel through the perfect vacuum of empty space, carrying energy and information across vast cosmic distances without needing any medium to support them. This wave carries energy through its oscillations, transferring power from one place to another without any physical matter actually moving between those locations. It is pure information in motion, a disturbance in the quantum fields that fill all of space. The frequency of these oscillations determines what kind of electromagnetic radiation we are dealing with, and what properties it will have when it interacts with matter. Low frequencies, oscillating thousands or millions of times per second, give us radio waves that can travel around the Earth by bouncing off the ionosphere. Slightly higher frequencies create microwaves that can heat food by making water molecules vibrate. Higher still, we get infrared radiation that we feel as heat from warm objects. Then comes visible light, oscillating hundreds of trillions of times per second, followed by ultraviolet light that can cause sunburns, X-rays that can penetrate soft tissue, and finally, gamma rays that can sterilize equipment and treat cancer. In the perfect vacuum of empty space, all electromagnetic waves, regardless of their frequency, travel at exactly the same speed. This speed, represented by the letter c, is 299,792,458 meters per second. This is not just a very fast speed, it is the ultimate speed limit of the universe, woven into the very structure of space-time itself by the laws of relativity. Nothing with mass can reach this speed because accelerating massive objects to the speed of light would require infinite energy, which is impossible. Nothing without mass can travel slower than this speed because massless particles have no choice but to move at c. This speed limit is not imposed by technology or engineering limitations. It is a fundamental feature of the universe itself, as basic and unchangeable as the existence of space and time. Photons are born moving at c, they live their entire existence at c, and if they are ever absorbed by matter, they die at c. This is not a choice or a preference or something that could be different under other circumstances. It is a fundamental law of nature, as inviolable as the law of gravity or the conservation of energy. Photons cannot slow down, speed up, or stop moving, at least not in the conventional sense. But here is where things get interesting, and where the first hints of the possibility of stopping light begin to emerge from the physics. When light enters a medium like water, glass, or air, something strange and wonderful happens that seems to contradict everything we have just established. The light appears to slow down dramatically, sometimes by factors of 2, 3, or even more. In water, light travels at about 225 million meters per second, roughly 3/4 the speed it has in vacuum. This is still incredibly fast by human standards, but measurably slower than c. In diamond, one of the most optically dense materials found in nature, light crawls along at only 124 million meters per second, less than half its vacuum speed. In some specially engineered materials, light can be slowed to speeds slow enough that you could outrun it on a bicycle. However, this is where our intuition misleads us, and understanding the truth behind this apparent slowing reveals the key to stopping light entirely. The individual photons making up the light beam are not actually slowing down at all. Each photon still moves at exactly c through the empty space between atoms in the medium. What creates the compelling illusion of slower light is a complex quantum mechanical dance of absorption and re-emission that happens trillions upon trillions of times per second. When a photon encounters an atom in the medium, the atom can absorb it completely, taking all of its energy into its electron structure. The atom then exists in what physicists call an excited state, with one or more electrons occupying higher energy levels than they normally would. This excited state is unstable and cannot last long. After a tiny fraction of a second, measured in femtoseconds or even attoseconds, the atom spontaneously returns to its ground state by re-emitting a new photon in the same direction as the original. This constant cycle of absorption and re-emission creates a delay in the overall progress of the light beam through the medium. The light beam as a whole appears to move more slowly, but each individual photon in the beam is still traveling at the cosmic speed limit between its interactions with atoms. The delay comes from the time each photon spends stored in the excited atoms, waiting to be re-emitted. Think of it like a relay race where each runner moves at full speed, but the handoffs between runners slow down the overall progress of the baton through the course. Or imagine trying to drive across a city during rush hour. Your car can still reach highway speeds between traffic lights, but the stops and starts at intersections slow your overall progress. The average speed of your trip is much less than the maximum speed of your car. This phenomenon gives us two different ways to think about the speed of light in materials, and this distinction is absolutely crucial for understanding how light can eventually be brought to a complete stop. There is the phase velocity, which describes how fast the individual wave crests move through the medium. This is related to how fast each photon travels between atoms. And there is the group velocity, which describes how fast a pulse of light energy containing actual information moves through the medium as a whole. The phase velocity in most materials is still quite close to c, because individual photons still move at light speed between interactions. But the group velocity can be much slower, because it includes the delays from absorption and re-emission. In normal materials like glass or water, both of these velocities are slower than c, but they are still quite fast by everyday standards. Light in window glass still moves at about 200 million meters per second, fast enough to circle the Earth 7.5 times in a single second. But what if we could engineer a medium so special, so precisely controlled at the quantum level, that we could make the group velocity not just slow, but actually zero? What if we could create conditions where light pulses could be completely stopped, with their photons absorbed by atoms and held there indefinitely, while still preserving all their quantum information, their energy, their phase relationships, everything that makes them what they are? This is where the real magic begins, and it requires us to enter the bizarre world of quantum mechanics and matter cooled to temperatures so cold they approach absolute zero. At these extreme conditions, atoms begin to behave in ways that seem to violate common sense, forming exotic states of matter that exist nowhere else in the known universe, except in the most sophisticated physics laboratories on Earth. The key insight that makes stopped light possible lies in understanding that light is not just energy moving through space. Light is information. Each photon carries quantum states, polarization, frequency, phase relationships, and countless other properties that define its identity as surely as DNA defines the identity of a living organism. By manipulating matter at the quantum level, using techniques that would have seemed like magic to scientists just 50 years ago, researchers have learned to transfer this information from moving photons into stationary atoms. This creates a kind of optical memory, a way to store light in matter like a computer stores data on a hard drive. The atoms become a repository for the quantum information that was previously racing through space at the speed of light. When the information is stored in this way, the light effectively stops moving, but it does not disappear. It waits, preserved in the quantum states of the atoms, ready to be released and continue its journey when the researchers choose to let it go. This is not science fiction. This is not theoretical speculation that might be possible someday in the distant future. This has been achieved in laboratories around the world, opening up possibilities that seemed impossible just decades ago. Scientists have taken pulses of laser light, brought them to a complete halt inside clouds of ultra-cold atoms, held them motionless for measurable periods of time, and then released them to continue propagating as if nothing had happened. But to understand how this miracle is accomplished, how the fastest thing in the universe can be convinced to stop and wait, we must first explore the strange world of slow light, where physicists first learned to tame the cosmic speed limit and bend it to their will. The journey to stopping light completely began with learning to slow it down, and this breakthrough came from one of the most extraordinary states of matter ever created in a laboratory. To understand how light can be frozen, we must first explore the bizarre world of ultra-cold atoms and the quantum mechanical phenomena that emerge when matter is cooled to temperatures so low they would make the coldest regions of outer space seem scorchingly hot. In 1999, at Harvard University, a Danish physicist named Line Hao achieved something that seemed impossible. She took a beam of laser light traveling at nearly 300 million meters per second and slowed it down to just 17 meters per second. That is slower than a car driving through a residential neighborhood. It was slower than a bicycle rider pedaling to work. For the first time in human history, light had been tamed to move at a speed you could literally outrun. But Howe did not accomplish this feat using any ordinary material. She used one of the strangest states of matter known to physics, something called a Bose-Einstein Condensate, or BEC for short. This exotic form of matter exists only under the most extreme conditions, and creating it requires technology that pushes the boundaries of what is physically possible with current scientific instruments. A Bose-Einstein condensate forms when a gas of atoms is cooled to temperatures incredibly close to absolute zero. Absolute zero, negative 273.15 degrees Celsius, is the coldest temperature theoretically possible in the universe. At this temperature, all atomic motion would cease completely. No atom has ever been cooled to exactly absolute zero, and the laws of quantum mechanics suggest it may be impossible to reach this ultimate cold, but scientists can get remarkably close. In Howe's experiments, the atoms were cooled to just a few billionths of a degree above absolute zero. At these unimaginably cold temperatures, something magical happens to the atoms. They begin to lose their individual identities and merge into a single quantum entity that behaves like one giant atom made of thousands or millions of smaller ones. This happens because of a quantum mechanical principle discovered by physicists Satyendra Nath Bose and Albert Einstein in the 1920s. They predicted that at sufficiently low temperatures, particles called bosons would all settle into the same quantum state, effectively becoming indistinguishable from one another. For decades, this remained a theoretical curiosity, something that existed only in the equations of quantum mechanics. The first Bose-Einstein condensate was finally created in 1995 by Eric Cornell and Carl Wieman at the University of Colorado and Wolfgang Ketterle at MIT. These scientists used sophisticated laser cooling and magnetic trapping techniques to cool rubidium and sodium atoms to the required temperatures. The achievement was so significant that Cornell, Wieman, and Ketterle shared the Nobel Prize in Physics in 2001. But Lena Howe realized that these ultra-cold atomic clouds could do more than just demonstrate exotic quantum behavior. She discovered that they could be used to manipulate light in ways that had never been possible before. The key lay in a quantum mechanical phenomenon called electromagnetically induced transparency, or EIT, a process that sounds like science fiction but is grounded in the deepest principles of quantum physics. Electromagnetically induced transparency works by using laser light to control how atoms interact with other light. Normally, when light of a specific frequency encounters atoms, those atoms will absorb the light if the frequency matches the energy difference between two of their electron energy levels. This is why different materials have different colors when they absorb some frequencies of light while reflecting others. But in an EIT system, a control laser is used to create quantum interference that prevents this absorption from occurring. The control laser creates a quantum superposition state in the atoms, where they exist in multiple energy configurations simultaneously. This superposition makes the atoms transparent to light that would normally be absorbed, hence the name electromagnetically induced transparency. More importantly for slowing light, the EIT process also dramatically changes the optical properties of the atomic medium. The quantum interference created by the control laser modifies something called the dispersion of the material, which determines how different frequencies of light travel through it. Under the right conditions, this modification can slow the group velocity of light pulses to extraordinarily low speeds. In Howe's groundbreaking experiment, she created a Bose-Einstein condensate of sodium atoms, and then used precisely tuned laser beams to create the EIT conditions. When she sent a pulse of probe light through this quantum-engineered medium, the light slowed from its normal vacuum speed of nearly 300 million meters per second to just 17 meters per second. The light pulse, which would normally travel several meters in the time it takes to blink an eye, now took several seconds to cross the same distance. This was not merely an academic curiosity or a demonstration of quantum mechanical principles. It was a practical achievement with profound implications for the future of technology. Light pulses slowed to such speeds could be manipulated, controlled, and processed in ways that had never been possible when they were moving at their normal cosmic velocities. But Howe and other researchers were not content to stop there. If light could be slowed to 17 meters per second, could it be slowed even further? Could the group velocity be reduced to just a few meters per second, or even less? The answer, as subsequent experiments would prove, was a resounding yes. Over the following years, researchers around the world began pushing the boundaries of slow light physics. They discovered that by fine-tuning the laser powers, the atomic densities, and the quantum states of their BEC systems, they could slow light to walking speed, then to crawling speed, then to speed so slow that the light pulses barely moved at all. In 2001, Howe's team achieved an even more remarkable feat. They managed to slow light pulses to speeds of less than 1 meter per second, slower than a person walking leisurely through a park. At these speeds, a light pulse that would normally cross a laboratory in a few nanoseconds now took several seconds to make the same journey. But the ultimate goal was becoming clear to physicists working in this field. If light could be slowed to 1 meter per second, why not slow it to 0? Why not stop light completely, bringing photons to a complete halt while preserving all their quantum information? The theoretical foundation for completely stopping light already existed in the physics of electromagnetically induced transparency. The same quantum interference effects that slowed light could, under the right conditions, bring it to a complete standstill. The challenge was engineering those conditions with sufficient precision and control. The breakthrough came when researchers realized that they could dynamically control the EIT process. Instead of maintaining constant laser powers and atomic conditions, they could gradually reduce the intensity of the control laser while a light pulse was traveling through the atomic medium. As the control laser intensity decreased, the light pulse would slow down more and more, until finally, when the control laser was turned off completely, the light pulse would stop entirely. But what happened to the light when it stopped? This was the key question that had to be answered before stopped light could become a practical reality. The answer lay in understanding the quantum mechanical relationship between light and matter in EIT systems. When the control laser is turned off and the light pulse stops, the quantum information carried by the light does not disappear. Instead, it is transferred to the atoms in the BEC. The quantum states of the light pulse, including its amplitude, phase, and frequency information, are mapped onto the quantum states of the atomic ensemble. The atoms essentially become a living memory of the stopped light pulse. This quantum state transfer is reversible. By turning the control laser back on, the researchers can transfer the quantum information back from the atoms to light, effectively recreating the original light pulse and allowing it to continue its journey through the medium and beyond. The light emerges from the atomic cloud, carrying the same information it had when it entered, as if it had been paused like a video recording. In 2001, Lene Howe's team accomplished this ultimate goal. They succeeded in bringing light pulses to a complete stop inside a BoseEinstein condensate, holding them motionless for a measurable period of time, and then releasing them to continue propagating. The stopped light maintained its quantum coherence and information content throughout the entire process. This achievement represented more than just a technical milestone. It demonstrated that light, the fundamental messenger of electromagnetic force and the defining feature of the cosmic speed limit, could be controlled and manipulated at the quantum level in ways that had previously been thought impossible. The implications were staggering. If light could be stopped and stored in atomic media, it opened up possibilities for optical computing, quantum information processing, and telecommunications technologies that could revolutionize how we handle information in the digital age. But stopping light for brief periods was only the beginning. The next challenge was to understand exactly what happens to light when it is frozen in place, how long it can be stored, and what this reveals about the fundamental nature of light itself. These questions would drive the next phase of research into one of the most counterintuitive phenomena in modern physics. The success of these early slow light and stopped light experiments also raised profound questions about the nature of time and information. If light, which plays such a fundamental role in defining the structure of space-time, according to Einstein's relativity, can be brought to a halt, what does this mean for our understanding of time itself? Does time stop for the information contained in the frozen light pulse? These questions go to the heart of some of the deepest mysteries in physics, touching on the relationship between quantum mechanics and relativity, the nature of information and entropy, and the fundamental structure of reality itself. The ability to stop light has given physicists a new tool for exploring these profound questions, and has opened up entirely new avenues of research that continue to yield surprising results. When we say that light has been stopped, what exactly do we mean? This question goes to the heart of one of the most profound and counterintuitive achievements in modern physics. To truly understand stopped light, we must dive deep into the quantum mechanical processes that make this seemingly impossible feat not only possible, but reproducible in laboratories around the world. The process of stopping light is fundamentally different from stopping any ordinary object. When you stop a car by applying the brakes, the kinetic energy of the moving vehicle is converted to heat through friction. The car's momentum is transferred to the earth through the contact between the tires and the road. The car comes to rest, sitting motionless until you choose to start it moving again. But light cannot be stopped in this conventional sense. Photons have no mass, so they cannot simply be brought to rest like a physical object. They cannot be grabbed, held, or stored in any traditional way. A photon is pure energy in motion, and according to the fundamental laws of physics, it must always move at the speed of light in vacuum. So when physicists say they have stopped light, they are describing something far more subtle and remarkable than merely bringing particles to a halt. What actually happens when light is stopped is a quantum mechanical magic trick of the most sophisticated kind. The light pulse does not simply slow down and stop like a ball rolling to a halt. Instead, the quantum information that defines the light pulse is transferred from the moving photons to the stationary atoms of the medium. The photons themselves are absorbed completely, their energy and information mapped onto the quantum states of the atomic ensemble. This process is called quantum state transfer, and it represents one of the most elegant demonstrations of quantum mechanics in action. Every property that defines the light pulse, its amplitude, its phase, its frequency characteristics, its polarization, even its quantum coherence properties, are encoded into the collective quantum state of thousands or millions of atoms in the stopping medium. Think of it like a message being translated from one language to another. The meaning and information content remain the same, but the form of the message changes completely. The light pulse, originally encoded as oscillating electromagnetic fields racing through space, is translated into a pattern of atomic excitations that can remain stationary for as long as the experimental conditions allow. The atoms in the medium effectively become a living photograph of the light pulse, preserving every detail of its quantum structure in their own quantum states. But unlike a photograph, which captures only a static image, this atomic storage preserves the dynamic properties of the light as well. When the stored information is eventually converted back to light, the recreated pulse carries the same energy, the same frequency, the same phase relationships it had before being stopped. This quantum state mapping is possible because of the deep connection between light and matter established by quantum mechanics. At the quantum level, the distinction between light and matter becomes blurred. Photons and atoms are both quantum objects that can exist in superposition states, entangled states, and other exotic quantum configurations. Under the right conditions, the quantum information can flow seamlessly between these different forms of matter and energy. The key to achieving this transfer lies in the precise control of electromagnetically induced transparency that we explored in the previous chapter. When the control laser that creates the EIT conditions is gradually reduced in intensity, it changes the optical properties of the atomic medium in real time. As the control laser dims, the group velocity of the light pulse decreases proportionally. Imagine the light pulse as a traveler moving through a medium that is becoming increasingly thick and viscous. As the medium becomes denser, the traveler moves more slowly until finally the medium becomes so thick that the traveler can no longer move at all. But instead of being trapped or destroyed, the traveler becomes part of the medium itself, preserving their identity and information until conditions change and they can resume their journey. When the control laser intensity reaches zero, the light pulse comes to a complete stop. At this moment, the quantum information is fully transferred to the atoms. The photons that made up the original pulse have been absorbed, but their quantum essence lives on in the atomic ensemble. The atoms collectively remember the light pulse, holding its information in their quantum states like a sophisticated biological memory system. The storage process is remarkably efficient. In well-designed experiments, nearly 100% of the light pulse's information can be transferred to the atoms with very little loss or degradation. This high fidelity is crucial for potential applications in quantum computing and quantum communication, where preserving the exact quantum state of information is essential for proper operation. But the most remarkable aspect of stopped light is that the process is completely reversible. The atomic memory of the light pulse can be read out at any time by turning the control laser back on. As the control laser intensity increases, the optical properties of the medium change again, and the quantum information stored in the atoms is transferred back to light. This readout process recreates the original light pulse with extraordinary precision. The emerging light has the same wavelength, the same intensity profile, the same phase relationships, and the same quantum properties as the light that was originally stopped. It is as if the light pulse was simply paused, like freezing a frame in a movie, and then allowed to resume playing. The time delay between stopping and releasing the light can be controlled by the experimenters. In early experiments, light pulses were stopped for microseconds or milliseconds. As techniques improved, researchers achieved storage times of seconds, then minutes. The current record for storing light in atomic media is approximately 60 seconds, achieved by Chinese researchers using clouds of cold rubidium atoms. During the storage period, the quantum information remains coherent in the atomic medium. Quantum coherence is a delicate property that describes how well the quantum relationships between different parts of a system are preserved. In most environments, quantum coherence is quickly destroyed by interactions with the surrounding environment, a process called decoherence. But in the ultra-cold, carefully controlled conditions of stopped light experiments, decoherence can be minimized. The atoms are isolated from external disturbances, maintained at temperatures near absolute zero, and shielded from electromagnetic interference. Under these pristine conditions, the quantum memory of the stopped light can persist for surprisingly long periods. The length of time that light can be stored depends on several factors. The temperature of the atomic medium is crucial, as thermal motion of the atoms can disrupt the delicate quantum states. The density of the atomic cloud also matters, as interactions between atoms can cause decoherence. External magnetic and electric fields must be carefully controlled, as they can shift the energy levels of the atoms and corrupt the stored information. Perhaps most importantly, the storage time depends on how well the atoms can be isolated from their environment. Every interaction with a stray photon, every collision with a background gas molecule, every fluctuation in the magnetic field can potentially destroy the stored quantum information. Creating the perfect conditions for long-term light storage is one of the greatest technical challenges in this field. But why is the ability to stop and store light so important? The implications go far beyond demonstrating quantum mechanical principles in the laboratory. Stopped light represents a new way to control and manipulate information at the quantum level, with potential applications that could revolutionize technology. In the realm of quantum computing, stopped light could serve as a quantum memory system, allowing quantum computers to store and retrieve quantum information with unprecedented precision. Current quantum computers are limited by how long they can maintain quantum coherence in their processing elements. If quantum information could be stored in stopped light systems and retrieved when needed, it could dramatically extend the computational capabilities of quantum machines. For quantum communication networks, stopped light offers the possibility of quantum routers and repeaters that could store quantum information temporarily while determining the best path for transmission. This could enable the construction of large-scale quantum internet systems that could revolutionize secure communication and distributed quantum computing. Even in classical optical communications, the ability to stop and store light pulses could lead to new types of optical buffers and delay lines that could improve the efficiency and functionality of fiber optic networks. Light pulses carrying digital information could be temporarily stored at network nodes, allowing for more sophisticated traffic management and error correction. But perhaps the most profound implication of stopped light is what it reveals about the nature of information itself. The fact that the complete quantum state of a light pulse can be transferred to atoms and later retrieved suggests that information has a reality that transcends the particular physical system that carries it. This touches on deep questions in physics about the relationship between information and reality. Some physicists argue that information is more fundamental than matter or energy, that the universe is essentially an information processing system where matter and energy are simply different ways of encoding and transmitting information. The stopped light experiments provide concrete evidence for this view. They show that information can exist independently of its physical carrier, that it can be translated between radically different physical systems while preserving its essential properties. The light pulse and the atomic ensemble are as different as a digital file and a hard drive, yet the information can move seamlessly between them. This also raises fascinating questions about the nature of time. When light is stopped, does time stop for the information it carries? From the perspective of the information encoded in the stopped light, no time passes during the storage period. The quantum state that emerges after storage is identical to the state that was stored, with no evidence that time has elapsed. This suggests that time, at least for quantum information, may not be the universal flowing entity that we experience in everyday life. Instead, time may be relative to the motion and interactions of the systems carrying information. When information is truly at rest, as in stopped light, time may effectively stand still for that information. These ideas connect stopped light experiments to some of the deepest mysteries in physics, including the nature of time in quantum mechanics, the relationship between information and entropy, and the fundamental structure of space-time itself. By learning to stop the fastest thing in the universe, physicists have opened a window into the most profound questions about the nature of reality. The ability to stop light and store its quantum information in atomic media has opened up one of the most exciting frontiers in modern technology: quantum memory systems, These devices represent a crucial missing piece in the development of practical quantum computers and quantum communication networks, technologies that promise to revolutionize everything from cryptography to drug discovery to artificial intelligence. To understand why stopped light is so important for quantum technology, we must first explore what makes quantum information fundamentally different from the classical information that powers our current computers and communication systems. Classical information, the kind used in smartphones, laptops, and the internet, is based on bits that can be either 0 or 1, on or off, present or absent. This binary system is simple, robust, and forms the foundation of all digital technology. Quantum information, however, operates according to the strange rules of quantum mechanics. Instead of classical bits, quantum computers use quantum bits, or qubits, that can exist in superposition states. A qubit can be 0, 1, or any quantum combination of both states simultaneously. This allows quantum computers to perform certain calculations exponentially faster than classical computers, potentially solving problems that would take classical machines millions of years to complete. But qubits are extraordinarily fragile. The quantum superposition states that give them their power are easily destroyed by interactions with the environment. Heat, electromagnetic radiation, vibrations, even cosmic rays can cause a qubit to lose its quantum properties in a process called decoherence. Most current quantum computers can maintain qubit coherence for only microseconds or milliseconds before the quantum information is lost. This fragility creates a fundamental problem for quantum computing. Many of the algorithms that could give quantum computers their revolutionary capabilities require the quantum information to remain coherent for much longer periods than current technology allows. Quantum error correction schemes exist to address this problem, but they require the ability to store and retrieve quantum information reliably over extended periods. This is where quantum memory systems become essential. A quantum memory is a device that can store the quantum state of a qubit, preserve it for an extended period, and then retrieve it on demand without destroying its quantum properties. It is like a quantum hard drive, capable of holding quantum information while maintaining the delicate superposition and entanglement relationships that make quantum computing possible. Stopped light systems represent one of the most promising approaches to building practical quantum memories. When a light pulse carrying quantum information is stopped in an atomic medium, all of the quantum properties of that information are preserved in the atomic ensemble. The atoms collectively remember not just the intensity and frequency of the light, but also its quantum phase relationships, its entanglement with other quantum systems, and its superposition states. The first demonstrations of quantum memory using stopped light focused on storing simple quantum states, such as single photons or weak laser pulses with well-defined quantum properties. Researchers showed that these quantum states could be stored in atomic media for microseconds or milliseconds, and then retrieved with high fidelity, meaning that the output quantum state was nearly identical to the input state. As the technology improved, researchers began storing more complex quantum states. They demonstrated the storage of entangled photon pairs, where two photons share quantum correlations that persist even when the photons are separated by large distances. Storing and retrieving entangled states is particularly challenging because any disruption to one photon affects its entangled partner, requiring exquisite control over the quantum memory system. One of the most significant breakthroughs came when researchers showed that stopped light quantum memories could store quantum superposition states with high fidelity. In these experiments, a single photon was prepared in a superposition of being in two different locations simultaneously. This quantum superposition was stored in an atomic ensemble and later retrieved, demonstrating that the strange quantum property of being in multiple states at once could be preserved through the storage and retrieval process. The efficiency of quantum memory systems is measured by several key parameters. Storage efficiency describes what fraction of the input quantum information is successfully stored in the atomic medium. Retrieval efficiency measures what fraction of the stored information can be recovered when the quantum state is read out. Storage time indicates how long the quantum information can be held before decoherence destroys it. Early stopped light quantum memories achieved storage and retrieval efficiencies of only a few %, meaning that most of the quantum information was lost during the storage process. But steady improvements in laser control, atomic preparation, and experimental techniques have pushed these efficiencies much higher. The best current systems can achieve storage efficiencies of over 90% and retrieval efficiencies of over 80%, making them practical for real-world quantum applications. The storage time has also improved dramatically. While early experiments could store quantum information for only microseconds, current systems can maintain quantum coherence for milliseconds or even seconds. Chinese researchers have achieved quantum storage times of over 1 minute using carefully prepared clouds of cold rubidium atoms, a duration long enough for many practical quantum computing applications. These improvements have been driven by a deeper understanding of the decoherence mechanisms that limit quantum memory performance. Researchers have identified the main sources of quantum information loss and developed techniques to minimize their effects. Temperature fluctuations, magnetic field variations, and collisions between atoms are among the primary culprits that destroy stored quantum states. To combat these effects, quantum memory experiments now use sophisticated environmental control systems. The atomic clouds are maintained at temperatures within microkelvin of absolute zero. Magnetic fields are stabilized to better than 1 part in a million, and the experimental chambers are isolated from vibrations and electromagnetic interference. These extreme measures are necessary to preserve the delicate quantum states for extended periods. The development of practical quantum memories has also benefited from advances in atomic physics and laser technology. New techniques for preparing atomic ensembles in precise quantum states have improved the uniformity and coherence of the storage medium. More stable and precise laser systems have enabled better control over the electromagnetically induced transparency processes that make light stopping possible. Different atomic species have been explored for quantum memory applications, each with their own advantages and challenges. Alkali atoms like rubidium and cesium are popular choices because they have simple electronic structures that are well understood and can be easily manipulated with lasers. Rare earth ions embedded in crystals offer potentially longer storage times but are more difficult to control. Trapped ion systems provide exquisite control over individual atoms but are challenging to scale to large numbers of qubits. The applications of quantum memory systems extend far beyond quantum computing. In quantum communication networks, quantum memories could serve as quantum repeaters, devices that extend the range of quantum communication by storing and retransmitting quantum information. Current quantum communication systems are limited to distances of a few hundred kilometers because quantum information cannot be amplified like classical signals without destroying its quantum properties. Quantum repeaters based on stopped light memories could overcome this limitation by storing quantum information at intermediate nodes in a communication network and then forwarding it to the next node. This would enable the construction of quantum internet systems spanning continents or even the entire globe, allowing for ultra-secure communication and distributed quantum computing applications. Another important application is in quantum sensing and metrology. Many of the most precise measurement techniques in physics rely on quantum interference effects that require maintaining quantum coherence over extended periods. Quantum memories could store reference quantum states for these measurements, allowing for unprecedented precision in detecting gravitational waves, measuring magnetic fields, or testing fundamental physical theories. The field of quantum memory is also driving advances in our understanding of the quantum classical boundary. By storing increasingly complex quantum states for longer and longer periods, researchers are exploring the limits of how quantum properties can be preserved in macroscopic systems. These experiments probe fundamental questions about why we observe classical behavior in everyday life despite living in a quantum universe. Recent experiments have demonstrated quantum memory of light pulses containing millions of photons, far larger than the single photon states typically studied in quantum optics. These experiments show that quantum properties can be preserved even in relatively large systems, blurring the line between the quantum and classical worlds. The storage of quantum information in atomic ensembles also provides insights into the nature of quantum entanglement and correlation. When a quantum state is stored in thousands or millions of atoms, the quantum information becomes distributed across the entire atomic ensemble. This creates complex many-body quantum states that are difficult to study in other systems. Researchers have used stopped light experiments to investigate how quantum information spreads through an atomic medium and how correlations between different parts of the system evolve over time. These studies are revealing new aspects of quantum many-body physics and providing insights that could lead to new quantum technologies. The ultimate goal of quantum memory research is to create devices that are fast, efficient, and long-lived enough to support practical quantum applications. Current systems are approaching this goal, with storage and retrieval times fast enough for quantum computing operations, efficiencies high enough to preserve quantum information reliably, and storage times long enough for complex quantum algorithms. As these technologies mature, stopped light quantum memories are expected to become essential components in the quantum computers and quantum communication networks of the future. They represent a bridge between the theoretical possibilities of quantum mechanics and the practical realities of building quantum technologies that can solve real-world problems. The success of stopped light quantum memories also demonstrates the power of fundamental physics research to drive technological innovation. The ability to stop light emerged from basic research into quantum mechanics and atomic physics, but it has evolved into a technology with the potential to transform computing, communication, and sensing in ways that would have been unimaginable just a few decades ago. The question of whether light can be stopped indefinitely touches on some of the most fundamental limits of physics and engineering. While scientists have successfully demonstrated the storage of light for minutes and even over an hour in laboratory conditions, the prospect of stopping light permanently raises profound questions about the nature of information, entropy, and the quantum mechanical foundations of reality itself. To understand the challenges of indefinite light storage, we must first examine what happens to quantum information over extended periods. Every quantum system, no matter how carefully isolated, eventually succumbs to the influence of its environment. This process, known as decoherence, represents one of the most fundamental limitations in quantum physics and sets ultimate bounds on how long quantum information can be preserved in any physical system. Decoherence occurs because perfect isolation from the environment is impossible in practice. Even in the most sophisticated laboratory conditions, atomic systems used for light storage interact with their surroundings in countless subtle ways. Thermal photons from the walls of the experimental chamber randomly strike the atoms, causing tiny but cumulative disruptions to their quantum states. Fluctuations in magnetic and electric fields, even at levels too small to detect with conventional instruments, gradually shift the energy levels of the atoms and corrupt the stored quantum information. The atoms themselves are not perfectly stationary, even at temperatures approaching absolute zero. Quantum mechanics mandates that atoms retain some residual motion even at the lowest possible temperatures, a phenomenon known as zero-point motion. This unavoidable movement causes the atoms to slowly drift apart, reducing the coherence of the atomic ensemble and degrading the quality of the stored light information over time. Perhaps most fundamentally, the Heisenberg uncertainty principle places fundamental limits on how precisely the quantum states of atoms can be defined and maintained. The more precisely we try to specify the quantum state of an atom, the more uncertain other properties become. This inherent quantum uncertainty propagates through the atomic ensemble over time, eventually destroying the delicate quantum correlations that preserve the stored light information. Despite these fundamental challenges, researchers have made remarkable progress in extending the storage time for stopped light. The key insight driving these improvements is that decoherence can be slowed, even if it cannot be eliminated entirely. By carefully engineering the atomic system and its environment, scientists can create conditions where quantum information degrades much more slowly than would occur naturally. One of the most important techniques for extending storage time is the use of decoherence-free subspaces. These are special quantum states that are naturally protected against certain types of environmental noise. By encoding the light information in these protected states, researchers can make the stored quantum information immune to many common sources of decoherence. For example, if magnetic field fluctuations are a major source of decoherence, the light information can be encoded in quantum states that are insensitive to magnetic fields. These states might involve symmetric superpositions of atomic configurations that respond identically to magnetic perturbations, cancelling out the effects of field fluctuations. Another powerful approach is the use of dynamical decoupling techniques. These methods apply carefully timed sequences of control pulses to the atomic ensemble, effectively reversing the effects of decoherence as they accumulate. It is similar to the way a spinning top can be kept upright by applying periodic nudges at just the right moments. By applying quantum control pulses at precisely calculated intervals, researchers can undo the damage caused by environmental interactions and maintain quantum coherence for much longer periods. The choice of atomic species also plays a crucial role in determining how long light can be stored. Different atoms have different sensitivities to environmental perturbations, and some are naturally more robust against decoherence than others. Atoms with simpler electronic structures tend to be less sensitive to environmental noise, while atoms with many electrons are more easily disrupted by external influences. Recent research has focused on rare earth ions embedded in crystalline hosts as particularly promising candidates for long-term light storage. These systems combine the advantages of atomic-level control with the stability of solid-state materials. The crystal lattice provides a rigid environment that minimizes atomic motion, while the rare earth ions retain the simple electronic structures that make them suitable for quantum storage applications. In 2022, a team of Chinese researchers achieved a landmark result by storing light in a cloud of cold rubidium atoms for over 60 seconds. This represented a 100-fold improvement over previous records and demonstrated that minute-long storage times are achievable with current technology. The experiment required extraordinary control over the atomic environment, including temperature stabilization to within microkelvin, magnetic field control to better than 1 part in 10 million, and isolation from external electromagnetic interference. But even this remarkable achievement falls far short of indefinite storage. The 60-second storage time was limited by residual decoherence effects that gradually degraded the stored quantum information. The researchers observed that the fidelity of the retrieved light pulse decreased exponentially with storage time, following the predictions of quantum decoherence theory. Theoretical calculations suggest that with perfect environmental control, storage times of hours or even days might be possible using current atomic systems. However, achieving such control would require technological capabilities that push far beyond what is currently feasible. The experimental apparatus would need to maintain temperature stability to nanokelvin levels, magnetic field stability to parts per billion, and complete isolation from all sources of electromagnetic noise. Even if such extreme conditions could be achieved, fundamental quantum mechanical limits would eventually impose absolute bounds on storage time. The uncertainty principle ensures that no quantum state can be preserved with perfect fidelity indefinitely. Over sufficiently long periods, quantum fluctuations will inevitably corrupt even the most carefully protected quantum information. Some physicists have proposed that truly indefinite light storage might require fundamentally different approaches that go beyond conventional atomic systems. One intriguing possibility is the use of topological quantum states, which are protected by fundamental symmetries of space and time rather than by environmental isolation. These exotic quantum states have been observed in certain solid-state materials and might provide natural immunity to decoherence. Topological protection works by encoding quantum information in global properties of a many-body quantum system that cannot be changed by local perturbations. Even if individual atoms in the system are disturbed by environmental noise, the global topological properties remain unchanged, preserving the stored quantum information. This approach has shown promise in theoretical studies, but experimental demonstrations remain challenging. Another speculative approach involves the use of quantum error correction codes, specifically designed for quantum memory applications. These codes would encode the light information redundantly across many atoms in such a way that decoherence in any subset of atoms could be detected and corrected without destroying the stored information. This would require sophisticated real-time feedback systems that could monitor the quantum state of the atomic ensemble and apply corrective operations as needed. The quest for indefinite light storage also intersects with fundamental questions about the nature of information and entropy in quantum mechanics. Some physicists argue that perfect information storage is prohibited by the second law of thermodynamics, which requires that entropy always increases in isolated systems. Storing quantum information perfectly for infinite time would violate this principle by preventing the natural increase of entropy that accompanies decoherence. However, other physicists contend that quantum information might be fundamentally different from classical information in ways that could allow for permanent storage under special conditions. The quantum no-cloning theorem, which states that arbitrary quantum states cannot be perfectly copied, might also play a role in determining the ultimate limits of quantum storage. Recent theoretical work has explored connections between quantum memory and the black hole information paradox, one of the most profound unsolved problems in theoretical physics. Some researchers suggest that understanding the ultimate limits of quantum storage might provide insights into how information is preserved when matter falls into black holes, potentially resolving one of the deepest mysteries in modern physics. The practical implications of extended light storage go far beyond academic curiosity. Even modest improvements in storage time could enable revolutionary applications in quantum technology. Storage times of minutes would make possible quantum memories for global quantum communication networks, allowing quantum information to be stored at relay stations while optimal transmission routes are calculated. Storage times of hours could enable quantum computers to solve problems that require long computational sequences, such as simulating complex chemical reactions or optimizing large-scale logistical problems. The ability to pause quantum computations and resume them later would fundamentally change how quantum algorithms are designed and executed. Storage times of days or longer could open up entirely new applications that we can barely imagine today. Quantum information could be stored and transported over vast distances, enabling quantum communication between Earth and space missions, or even between different planets. Scientific instruments could store quantum reference states for years, enabling precision measurements that would otherwise be impossible. The development of practical long-term quantum storage also faces significant engineering challenges beyond the fundamental physics limitations. The experimental apparatus required for extended light storage is extraordinarily complex and expensive, involving sophisticated laser systems, ultra-high vacuum chambers, magnetic shielding, and vibration isolation. Making such systems practical for real-world applications will require major advances in engineering and manufacturing. Current quantum memory experiments typically require teams of highly skilled physicists and elaborate laboratory facilities that cost millions of dollars to construct and operate. For quantum storage to become a practical technology, these systems will need to become much simpler, more robust, and less expensive. This will likely require the development of new materials, new fabrication techniques, and new approaches to quantum control that are more suitable for commercial applications. The miniaturization of quantum memory systems represents another major challenge. Current experiments use atomic clouds that are millimeters or centimeters in size, far too large for integration into practical quantum devices. Future quantum memories will need to be shrunk to micrometer or nanometer scales while maintaining their quantum storage capabilities. Some researchers are exploring the use of single atoms or small clusters of atoms as quantum memories, potentially allowing for dramatic miniaturization. Others are investigating solid-state systems based on quantum dots or color centers in diamonds, which might be more suitable for integration into semiconductor devices. The scalability of quantum memory systems is also a crucial consideration. While current experiments typically store the quantum state of a single light pulse, practical quantum applications will require the simultaneous storage of thousands or millions of quantum states. This will require the development of massively parallel quantum memory systems that can handle many quantum channels simultaneously without crosstalk or interference. Despite these challenges, the steady progress in quantum memory research gives reason for optimism about the future of long-term light storage. Storage times have improved by many orders of magnitude over the past 2 decades, and there is no fundamental reason why this progress cannot continue. While truly indefinite storage may remain elusive, storage times of hours, days, or even longer may become achievable within the coming decades. The pursuit of indefinite light storage is also driving advances in our fundamental understanding of quantum mechanics and thermodynamics. By pushing the limits of how long quantum information can be preserved, researchers are exploring the deepest principles that govern information, entropy, and time in quantum systems. These investigations may ultimately lead to new physics that revolutionizes our understanding of reality itself. As we continue to push the boundaries of what is possible with stopped light, we are not just developing new technologies, but also probing the fundamental nature of information and time in our universe. The quest to stop light indefinitely may ultimately teach us as much about the nature of reality as it does about the practical possibilities of quantum technology. This question strikes at the heart of one of the most fascinating thought experiments in modern physics. If light can truly be stopped and held motionless in an atomic medium, what would happen if you walked past it? Could you literally overtake light, the universe's ultimate speed limit? Would this create a paradox that breaks the laws of relativity? The answers reveal profound truths about the nature of light, motion, and the structure of space-time itself. To understand what happens when you pass frozen light, we must first be completely clear about what we mean by light being stopped. As we have explored in previous chapters, stopping light does not mean that photons are sitting motionless in space like parked cars on a highway. Instead, the quantum information that defines the light pulse has been transferred from moving photons to stationary atoms in the storage medium. When light is stopped using electromagnetically induced transparency in a Bose-Einstein condensate, the original photons are completely absorbed by the atoms. The light pulse ceases to exist as electromagnetic radiation racing through space. Instead, its quantum essence, all the information that defined its properties, becomes encoded in the collective quantum state of thousands or millions of atoms in the ultra-cold atomic cloud. This distinction is crucial for understanding what happens when you move past the stopped light. You are not actually passing photons that are moving slower than you are. You are moving past a collection of atoms that happen to be storing quantum information in their internal energy states. From a relativistic perspective, there is nothing unusual about moving past a stationary collection of atoms, regardless of what information they might be storing. Imagine you are walking through a library, past shelves filled with books. The books contain vast amounts of information, stories, scientific knowledge, human wisdom accumulated over centuries. But the physical act of walking past these books does not create any paradox, even though you are moving faster than the information stored in them. The information in the books is not moving at all. It is simply encoded in the arrangement of ink on paper, waiting to be read when someone opens a book. Stopped light is similar. The quantum information that was once racing through space at 300 million meters per second is now stored in the quantum states of atoms, completely at rest relative to the laboratory frame. When you walk past the atomic cloud containing this stored information, you are simply moving past atoms, not overtaking light in any meaningful sense. But let us explore this scenario in more detail to understand the full implications. Imagine a sophisticated laboratory where researchers have successfully stopped a light pulse in a cloud of ultra-cold atoms. The pulse, which originally contained millions of photons carrying a specific message encoded in their quantum states, is now stored as a complex pattern of atomic excitations in the BoseEinstein Condensate. As you walk through the laboratory, you approach the region where the light is stored. From your perspective, you see a small cloud of atoms suspended in an optical trap, glowing faintly from the laser beams used to maintain the storage conditions. The cloud appears perfectly ordinary, perhaps a few millimeters across, containing perhaps 1 million sodium or rubidium atoms cooled to temperatures measured in nanokelvin. As you pass by this atomic cloud, you are indeed moving faster than the stored light information. If you are walking at a typical speed of 1 meter per second, you are moving faster than the light would be traveling if it were propagating through the storage medium. In the most dramatic slow light experiments, light has been slowed to speeds of just a few meters per second, well within the range of human locomotion. But your motion past the stored light creates no paradox and violates no physical laws. The light information is not propagating through space. So there is no sense in which you are outrunning electromagnetic radiation. You are simply moving past a quantum memory device that happens to be storing information that was once carried by light. The situation becomes even more interesting when we consider what happens from different reference frames. According to Einstein's special theory of relativity, there is no absolute reference frame for motion. Your motion relative to the stored light must be considered from the perspective of different observers who might be moving at different velocities. From the perspective of an observer at rest in the laboratory, you are moving past stationary atoms that contain stored light information. From your perspective, as you walk past the atomic cloud, the atoms are moving backward relative to you. But in neither case is there any violation of the principle that nothing can move faster than light in vacuum, because the light information is not moving through space at all. The relativistic analysis becomes more subtle when we consider what happens when the stored light is eventually released. Suppose that just as you finish walking past the atomic cloud, the researchers turn their control laser back on and release the stored light pulse. The light emerges from the atomic cloud and begins propagating through space at the speed appropriate for the medium it encounters. If the light emerges into vacuum, it will immediately accelerate to the full speed of light, approximately 300 million meters per second. If it emerges into air or another medium, it will travel at the speed characteristic of that medium. In either case, the light will quickly outpace your walking speed and continue on its journey as if the storage episode had never occurred. From your perspective, it might appear that light suddenly materialized in front of you and then rapidly accelerated away. But this appearance is deceiving. The light did not violate causality or special relativity. It simply emerged from a storage device and resumed its natural motion at the speed dictated by the medium it found itself in. The quantum mechanical description of this process reveals even more fascinating details. When light is stored in an atomic medium, the quantum information becomes entangled with the internal states of many atoms. The stored information is not localized to any particular atom, but is distributed across the entire atomic ensemble in a complex quantum superposition state. When you walk past this quantum system, your motion does not directly affect the stored quantum information. The atoms continue to preserve the light pulse information in their quantum states, regardless of any external motion relative to the laboratory. Quantum information, unlike classical information, can be remarkably robust against many types of external perturbations. However, your motion could potentially affect the storage system in subtle ways. If you carry any magnetic materials or electronic devices, the electromagnetic fields they produce could potentially disturb the delicate quantum states of the atoms. The ultra-cold atoms used in light storage experiments are exquisitely sensitive to external electromagnetic fields, and even tiny perturbations can disrupt the storage process. In practice, researchers conducting stopped light experiments go to extraordinary lengths to shield their atomic systems from external disturbances. The experimental chambers are typically surrounded by multiple layers of magnetic shielding, and access to the laboratory during sensitive measurements is strictly controlled. Even the presence of a person walking near the experiment could potentially introduce enough electromagnetic noise to disrupt the quantum storage. But assuming perfect isolation, your passage past the stored light would have no effect on the quantum information itself. The atoms would continue to preserve the light pulse data in their internal states, ready to release it when the researchers choose to apply the appropriate control fields. The question of passing frozen light also raises interesting considerations about the nature of information and its relationship to motion. In our everyday experience, information typically moves from one place to another by being carried by some physical medium. Sound waves carry acoustic information through air, radio waves carry electromagnetic information through space, and data packets carry digital information through fiber optic cables. But when light is stopped, the information becomes divorced from any moving carrier. It exists as a static pattern encoded in the quantum states of stationary atoms. This suggests that information itself is more fundamental than the particular physical systems that carry it, an idea that has profound implications for our understanding of physics and computation. Some physicists have speculated that this property of quantum information could be exploited for novel forms of data storage and processing. If information can exist independently of motion, it might be possible to manipulate and process it in ways that are not constrained by the usual speed limits that apply to moving particles and waves. The concept of passing stopped light also connects to broader questions about the nature of time and simultaneity in physics. When light is stored in an atomic medium, it exists in a kind of temporal limbo. From the perspective of the information itself, no time passes during the storage period. The quantum state that emerges when the light is released is identical to the state that was stored, with no indication that time has elapsed. This raises philosophical questions about whether time is universal or relative to the motion and interactions of physical systems. If time can effectively stop for stored quantum information, what does this tell us about the fundamental nature of time itself? Einstein's theory of relativity already tells us that time is relative, that clocks moving at different velocities will measure different elapsed times for the same sequence of events. The stopped light experiments add another dimension to this relativity by showing that time can effectively stand still for information that is not propagating through space. The practical implications of these ideas are still being explored by researchers around the world. The ability to store and release light at will could lead to new types of optical devices that manipulate time as well as space. Optical delay lines based on stopped light could create programmable time delays for optical signals, allowing for sophisticated signal processing applications. More speculatively, some researchers have proposed that stopped light systems could be used to create temporal analogues of spatial optical devices. Just as lenses and mirrors manipulate the spatial properties of light beams, these temporal devices could manipulate the time evolution of optical signals, potentially leading to new forms of optical computing and signal processing. The quantum mechanical aspects of stopped light also open up possibilities for exploring the relationship between quantum mechanics and relativity in new ways. The fact that quantum information can be stored in stationary atoms while preserving its quantum properties provides a unique laboratory for testing how quantum mechanics behaves in different reference frames. Some recent experiments have explored what happens when the entire stopped light system is accelerated or rotated while the light information is stored. These experiments probe whether quantum entanglement and other quantum properties are affected by the motion of the storage medium, potentially providing new tests of fundamental physical principles. The question of passing stopped light ultimately illustrates the subtle but crucial distinction between information and the physical systems that carry it. When you walk past a cloud of atoms storing light information, you are not violating the speed of light because the light itself is not moving. The information that once raced through space at cosmic velocities now exists as a static pattern in quantum states, as motionless as words written on a page. This realization helps us understand that the speed of light is not just a speed limit for moving objects, but a fundamental feature of how information and causality propagate through space-time. When information is stored in stationary systems, these constraints no longer apply in the same way, opening up new possibilities for manipulating and controlling information in ways that were previously impossible. As our understanding of stopped light and quantum storage continues to advance, we may discover even more surprising connections between motion, information, and the fundamental structure of reality. The simple act of walking past frozen light reveals depths of physics that continue to challenge our intuitions about the nature of space, time, and information in the quantum universe. The ability to stop light has captured the imagination of scientists and science fiction enthusiasts alike, raising tantalizing questions about whether this remarkable achievement could somehow lead to faster than light travel or time travel. These possibilities touch on humanity's deepest fantasies about transcending the limitations of space and time, but they also probe the fundamental boundaries of what is physically possible in our universe. To address these questions properly, we must first understand exactly what the speed of light represents in the context of Einstein's special theory of relativity. The speed of light in vacuum, denoted by the letter c, is not merely the fastest speed at which photons happen to travel. It is a fundamental feature of space-time itself, determining the structure of causality and the relationship between space and time throughout the universe. Einstein's revolutionary insight was that the speed of light represents the maximum rate at which any information or causal influence can propagate through space. This speed limit is built into the very geometry of space-time, establishing what physicists call the light cone structure that determines which events can influence which other events. Nothing can travel faster than light because doing so would violate causality, potentially allowing effects to precede their causes and creating logical paradoxes that would undermine the consistency of physical law. When we say that light has been stopped in laboratory experiments, we must be extremely careful about what this means in the context of relativity. The photons that make up the light pulse are indeed brought to rest, but this occurs through a process that fundamentally changes their nature. The photons are absorbed by atoms in the storage medium, and their quantum information is transferred to the internal states of those atoms. Crucially, this process does not violate the speed limit imposed by special relativity. The individual photons still travel at exactly c, right up until the moment they are absorbed by the atoms. They do not slow down gradually and then stop, like a car coming to rest at a traffic light. Instead, they are instantaneously converted from photons, moving at c, to quantum information stored in stationary atomic states. This distinction is fundamental to understanding why stopped light experiments do not provide a pathway to faster-than-light travel. The speed of light barrier is not something that can be circumvented by clever experimental tricks or exotic states of matter. It is a consequence of the deep structure of space-time itself, as inviolable as the laws of mathematics. However, the manipulation of light in exotic media does raise subtle questions about the relationship between different velocities that can be defined for electromagnetic waves. We have already discussed the distinction between phase velocity and group velocity in dispersive media. In certain specially engineered materials, these velocities can behave in ways that seem to challenge our intuitions about the speed of light. For example, in some metamaterials with unusual optical properties, the group velocity of light pulses can actually exceed c, the speed of light in vacuum. This might seem to violate relativity, but careful analysis shows that no information actually travels faster than c in these systems. The group velocity exceeds c only because the shape of the light pulse is distorted as it passes through the medium, not because any part of the pulse actually moves superluminally. These phenomena demonstrate the subtlety required when discussing the speed of light in complex media. The fundamental prohibition against faster-than-light travel applies specifically to the transmission of information or causal influences, not necessarily to every velocity that can be mathematically defined for electromagnetic waves in exotic materials. Similarly, some experiments have achieved negative group velocities, where light pulses appear to exit a medium before they finish entering it. This creates the strange situation where the peak of the output pulse emerges from the far side of the material before the peak of the input pulse has fully entered the near side. Again, this apparent violation of causality is resolved when we recognize that no information actually travels faster than light. The negative group velocity arises from the reshaping of the pulse by the medium, not from superluminal information transfer. These exotic velocity effects in specially engineered materials have led some researchers to speculate about possible applications for faster-than-light communication or even time travel. If light pulses can be made to exit a medium before they finish entering it, perhaps this effect could be amplified or exploited in some way to send information into the past. However, detailed theoretical analysis of these systems consistently shows that the apparent violations of causality are illusory when the complete electromagnetic field is analyzed, including all the subtle components that are often neglected in simplified treatments. The causal structure remains intact. Information and energy still propagate at speeds no greater than c, preserving the consistency of relativity. The stopped light experiments add another layer to these discussions. By bringing light to a complete halt and then releasing it after a controllable delay, researchers have demonstrated unprecedented control over the timing of optical signals. This raises the question of whether such control could somehow be exploited to create causal loops or other time travel scenarios. The answer, unfortunately for science fiction fans, is no. The ability to store and release light does not provide a mechanism for sending information into the past or violating causality. When light is stopped and later released, it continues its journey from the point where it was stored, carrying the same information it had when it was originally absorbed. The storage and release process simply inserts a controllable delay into the light's trajectory, analogous to putting a letter in a filing cabinet and retrieving it later. To understand why stopped light cannot enable time travel, we need to consider what time travel would actually require from a physics perspective. Science fiction often portrays time travel as simply moving very fast or manipulating space and time in some dramatic way. But the reality is much more subtle and, unfortunately for would-be time travelers, much more restrictive. Einstein's general theory of relativity does permit certain exotic spacetime geometries that could, in principle, allow for time travel. These include rotating black holes, traversable wormholes, and cosmic strings moving at relativistic speeds. However, all of these scenarios require extreme conditions involving massive gravitational fields, negative energy densities, or other phenomena that are far beyond current technological capabilities. More importantly, these exotic spacetime geometries would need to affect the entire region of space where time travel is desired, not just the behavior of light within that region. Manipulating light alone, no matter how cleverly, cannot alter the causal structure of spacetime itself. The stopped light experiments operate entirely within the framework of normal spacetime, using quantum mechanical effects to control the propagation of electromagnetic radiation without affecting the underlying geometry of space and time. The quantum mechanical nature of the light storage process also places fundamental limits on what information can be extracted from the stored light. The quantum no-cloning theorem, one of the fundamental principles of quantum mechanics, states that arbitrary quantum states cannot be perfectly copied. This means that the quantum information stored in stopped light experiments cannot be duplicated or amplified in ways that might enable causal violations. Furthermore, the process of storing and retrieving light necessarily involves some loss of information due to decoherence and other quantum mechanical effects. Even the most efficient quantum memory systems cannot preserve quantum states with perfect fidelity indefinitely. This fundamental limitation ensures that the stored light cannot carry perfect information about future events back to earlier times, even if such backwards time transmission were somehow possible. The question of faster-than-light travel through stopped light manipulation is equally problematic from a theoretical perspective. While light can indeed be slowed to arbitrarily low speeds in appropriately engineered media, this does not provide a mechanism for accelerating other objects beyond the speed of light. The slow light effects are specific to electromagnetic radiation in particular media and do not extend to massive particles or other forms of matter and energy. Some researchers have explored whether the techniques used to slow and stop light might be applicable to other types of waves or particles. For example, similar effects have been demonstrated with sound waves, where acoustic pulses can be slowed, stopped, and released in acoustic media. However, these acoustic analogues do not provide any fundamental new insights into the nature of the relativistic speed limit, as sound waves are not constrained by special relativity in the same way that electromagnetic waves are. The possibility of using quantum entanglement, which can be preserved in stopped light systems, for faster-than-light communication has also been extensively studied. Quantum entanglement allows particles to exhibit correlations that appear to violate the speed of light limit, with measurements on one particle instantaneously affecting the state of its entangled partner, regardless of the distance between them. However, detailed analysis shows that quantum entanglement cannot be used to transmit information faster than light. The correlations between entangled particles are fundamentally random from the perspective of any individual observer. While the correlations themselves are established instantaneously, extracting useful information from them requires classical communication channels that are limited by the speed of light. The stopped light experiments have enabled researchers to study quantum entanglement in new ways, including the storage and retrieval of entangled photon pairs. These experiments have confirmed that entanglement can be preserved through the storage process, but they have not revealed any new mechanisms for superluminal information transfer. Despite the inability to achieve faster-than-light travel or time travel through stopped light, these experiments have opened up remarkable new possibilities for controlling the flow of information through space and time. The ability to store light for controllable periods allows for the creation of optical delay lines with unprecedented precision and flexibility. These optical delay lines could enable new forms of optical signal processing that were previously impossible. For example, multiple light pulses could be stored simultaneously, and then released in any desired sequence, allowing for complex temporal manipulations of optical information. Such capabilities could revolutionize optical computing and telecommunications in ways that are only beginning to be explored. The precise control over light propagation, enabled by stoplight techniques, also opens up possibilities for testing fundamental physical principles in new ways. Researchers can now study how quantum mechanical effects evolve over precisely controlled time intervals, potentially revealing new insights into the nature of quantum mechanics and its relationship to relativity. Some theoretical physicists have speculated that advanced civilizations with technology far beyond our current capabilities might find ways to exploit quantum mechanical effects for forms of transportation or communication that circumvent the apparent limitations of relativity. However, such speculations remain firmly in the realm of science fiction, with no clear theoretical pathway from current stopped light experiments to such exotic applications. The search for faster-than-light travel and time travel continues to motivate research in theoretical physics, particularly in areas such as quantum gravity and cosmology, where the laws of physics are still not fully understood. Some theories of quantum gravity suggest that the structure of space-time itself might be more flexible than general relativity implies, potentially allowing for exotic phenomena that could enable new forms of transportation or communication. However, these theoretical possibilities remain highly speculative and are not supported by any current experimental evidence. The stopped light experiments, remarkable as they are, operate entirely within the well-established framework of quantum mechanics and special relativity, without challenging the fundamental speed limits imposed by these theories. In conclusion, while the ability to stop and manipulate light represents a stunning achievement in experimental physics with profound implications for technology and our understanding of quantum mechanics, it does not provide a pathway to faster-than-light travel or time travel. The fundamental structure of space-time, as described by Einstein's theories of relativity, remains inviolate. The speed of light continues to represent the ultimate speed limit for information and causal influences, regardless of how cleverly we learn to manipulate electromagnetic radiation in exotic quantum media. The true significance of stopped light lies not in its potential to violate the laws of physics, but in its demonstration of the extraordinary control that quantum mechanics allows us to exercise over the fundamental constituents of reality. These experiments reveal new possibilities for information processing, quantum computing, and scientific investigation that could transform technology and deepen our understanding of the universe in ways we are only beginning to imagine. The ability to stop light has opened an extraordinary window into one of the most profound and mysterious aspects of our universe, the nature of time itself. When physicists freeze a beam of light in place, they are not merely demonstrating technical mastery over electromagnetic radiation. They are probing the deepest foundations of reality, exploring questions that have puzzled philosophers and scientists for millennia about what time really is and how it relates to the physical world. Time is perhaps the most familiar yet least understood aspect of human experience. We live immersed in time, aging moment by moment, watching the world change around us in an endless flow from past to future. Yet, when we try to understand what time actually is, we encounter profound mysteries that challenge our most basic assumptions about reality. Ancient philosophers debated whether time was absolute and universal, flowing at the same rate throughout the universe, or whether it might be relative and dependent on the observer. Aristotle argued that time was the measure of change, existing only insofar as things moved and transformed. Plato suggested that time was a moving image of eternity, a shadow cast by perfect and timeless forms into the imperfect world of physical existence. These philosophical debates took on new urgency and precision with the development of modern physics. Isaac Newton conceived of time as absolute and universal, flowing uniformly throughout the cosmos, regardless of what happened within it. In Newton's universe, time was like a great cosmic clock, ticking away at the same rate everywhere, providing a universal standard against which all motion and change could be measured. But Einstein's revolutionary theories of relativity shattered this comfortable notion of absolute time. Special relativity revealed that time is relative to the observer, flowing at different rates for objects moving at different velocities. Time dilation effects mean that a clock moving at high speed will run slower than a stationary clock, with the difference becoming more pronounced as speeds approach the speed of light. General relativity went even further, showing that time is affected by gravity and the curvature of space-time. Clocks run slower in stronger gravitational fields, an effect that has been precisely measured and must be accounted for in the global positioning system satellites that enable modern navigation technology. These relativistic effects established that time is not the fixed, universal backdrop that Newton imagined, but rather a dynamic aspect of space-time that can be stretched, compressed, and warped by motion and gravity. Yet even Einstein's theories leave fundamental questions about time unanswered. What gives time its apparent direction from past to future? Why do we remember the past but not the future? What determines the rate at which time flows? The stopped light experiments add a fascinating new dimension to these questions by demonstrating situations where time appears to stand still for certain physical systems. When a light pulse is frozen in an atomic medium, the quantum information it carries exists in a kind of temporal suspension, unchanged and unchanging until the moment it is released to continue its journey. From the perspective of the stored quantum information, no time passes during the storage period. The quantum state that emerges when the light is released is identical to the state that was stored, showing no evidence that time has elapsed. It is as if the information exists outside of time during the storage period, preserved in a quantum amber that isolates it from the normal flow of temporal change. This raises profound questions about the relationship between time and information. If information can be isolated from the flow of time, what does this tell us about the fundamental nature of both? Some physicists argue that time and information are intimately connected, that the flow of time is fundamentally about the processing and transformation of information throughout the universe. This information-theoretic view of time suggests that time emerges from the countless interactions between quantum systems that constantly process and exchange information. From this perspective, time is not a fundamental feature of reality, but rather an emergent property that arises from the complex dynamics of information flow in quantum systems. The stopped light experiments provide a unique laboratory for testing these ideas. By isolating quantum information from the normal processes of interaction and change, researchers can study how time behaves when information processing is temporarily suspended. These studies are revealing new insights into the relationship between quantum mechanics and temporal evolution. One of the most striking aspects of stopped light is how it challenges our intuitive understanding of temporal flow. In our everyday experience, time seems to flow uniformly and continuously, like a river carrying everything along at the same rate. But the ability to pause quantum information suggests that time might be more like a series of discrete steps, with the possibility of inserting arbitrary delays into the temporal sequence of events. This discretization of time has deep connections to fundamental questions in quantum mechanics about the nature of measurement and observation. The quantum measurement problem, one of the most profound unsolved issues in physics, concerns how and when the smooth evolution of quantum states transitions into the discrete outcomes we observe in experiments. Some interpretations of quantum mechanics suggest that time itself might be quantized, broken up into discrete units rather than flowing continuously. The stopped light experiments do not directly test this idea, but they do demonstrate that quantum evolution can be interrupted and resumed in ways that seem inconsistent with naive notions of continuous temporal flow. The relationship between time and causality also takes on new dimensions in the context of stopped light. Causality, the principle that effects must follow their causes, is intimately connected to the structure of time and the speed of light limit. The fact that light can be stopped without violating causality tells us something important about how temporal ordering is maintained in quantum systems. When light is stored in an atomic medium, the causal relationships between events are preserved even though the normal propagation of information is interrupted. The quantum information that emerges from storage maintains the same causal structure it had when it entered storage, suggesting that causality is more fundamental than the particular mechanisms by which information propagates through space and time. This has implications for our understanding of free will and determinism, philosophical questions that have been debated for centuries. If quantum information can be paused and resumed without affecting its causal structure, this suggests that the universe might have a kind of temporal flexibility that allows for more complex relationships between cause and effect than traditional deterministic models would suggest. The stopped light experiments also illuminate the relationship between time and entropy, the measure of disorder in physical systems. The second law of thermodynamics states that entropy always increases over time in isolated systems, providing what many physicists consider to be the fundamental arrow of time that distinguishes past from future. But when quantum information is stored in stopped light systems, its entropy appears to remain constant during the storage period. The quantum state emerges from storage with the same degree of order and information content it had when it entered storage, suggesting that the normal increase of entropy has been suspended along with the normal flow of time. This raises fascinating questions about whether the arrow of time is truly fundamental, or whether it is an emergent property that can be temporarily suspended under special conditions. Some theoretical physicists have proposed that time reversal might be possible in quantum systems under certain circumstances, and the stopped light experiments provide a concrete example of quantum temporal manipulation that could inform these speculations. The precision with which time can be controlled in stopped light experiments has also enabled new tests of fundamental physical principles. Researchers can now study how quantum mechanical effects evolve over precisely controlled time intervals, potentially revealing departures from standard quantum mechanical predictions that could indicate new physics. For example, some theories of quantum gravity predict that the smooth evolution of quantum states might be modified by gravitational effects at very small scales. By studying how stored quantum information evolves over different time periods, researchers might be able to detect these subtle effects and gain insights into the quantum nature of gravity. The stopped light experiments have also provided new ways to study the relationship between quantum mechanics and special relativity. The fact that quantum information can be stored and retrieved while preserving relativistic causality demonstrates the deep compatibility between these two fundamental theories, but it also reveals new subtleties in how they interact. Some recent experiments have explored what happens when the entire stopped light system is accelerated while quantum information is stored. These studies probe whether quantum entanglement and other quantum properties are affected by the motion of the storage medium, potentially providing new tests of how quantum mechanics behaves in accelerated reference frames. The philosophical implications of these experiments extend far beyond physics into fundamental questions about the nature of reality and consciousness. If time can be stopped for quantum information, what does this mean for our understanding of consciousness and subjective experience, which seems so intimately connected to the flow of time? Some philosophers and physicists have speculated that consciousness itself might be related to quantum information processing in the brain. If this is true, then understanding how quantum information behaves in temporal suspension could provide insights into the nature of conscious experience and the relationship between mind and time. The stopped light experiments also raise questions about the nature of memory and information storage in biological systems. If quantum information can be perfectly preserved over extended periods in artificial systems, might biological evolution have found ways to exploit similar principles for long-term memory storage? These speculations remain highly controversial and are not supported by direct experimental evidence. However, they illustrate how the stopped light experiments are opening up new ways of thinking about some of the most fundamental questions in science and philosophy. The technological implications of temporal control over quantum information are equally profound. The ability to pause and resume quantum evolution with high precision could enable new forms of quantum computing that operate according to fundamentally different principles than current approaches. Traditional quantum computers attempt to perform calculations as quickly as possible before decoherence destroys the quantum information. But stopped light quantum memories could allow for quantum computers that pause their calculations, store intermediate results, and resume computation when conditions are optimal. This could dramatically expand the types of problems that quantum computers can solve. The precise temporal control enabled by stopped light could also lead to new forms of quantum communication networks that manipulate time as well as space. Messages could be stored at network nodes for precisely controlled periods, allowing for sophisticated scheduling and routing algorithms that optimize information delivery across both spatial and temporal dimensions. Even more speculatively, some researchers have proposed that advanced control over quantum temporal evolution could lead to new forms of artificial intelligence that process information according to fundamentally different temporal principles than biological intelligence. Such systems might be able to pause their thought processes, consider problems over extended periods, and resume thinking when new information becomes available. The stopped light experiments are also providing new insights into the fundamental nature of physical law and the structure of scientific explanation. The ability to manipulate time at the quantum level demonstrates that the universe is far more flexible and controllable than our everyday experience might suggest. This flexibility raises profound questions about the relationship between the laws of physics and the phenomena they describe. Are the laws of physics fundamental constraints that cannot be violated? Or are they emergent patterns that can be transcended through sufficiently advanced understanding and technology? The stopped light experiments suggest that many apparent constraints in physics are actually consequences of our limited ability to manipulate quantum systems rather than fundamental limitations of nature. As our technological capabilities advance, we may discover that reality is far more malleable than we currently imagine. The study of time through stopped light experiments is also revealing new connections between different areas of physics that were previously thought to be unrelated. The relationship between quantum mechanics and general relativity, the nature of information and entropy, the structure of causality and temporal ordering all appear to be more deeply interconnected than previously recognized. These connections suggest that our understanding of time may require a more unified theoretical framework that encompasses quantum mechanics, relativity, thermodynamics, and information theory. The stopped light experiments are providing crucial experimental data that could guide the development of such a unified theory. As research into stopped light and quantum temporal control continues to advance, we can expect even more surprising discoveries about the nature of time and its relationship to the fundamental structure of reality. The ability to freeze light has given us a new tool for probing some of the deepest mysteries of existence, and we are only beginning to explore its full potential for revealing the secrets of time itself. While physicists have achieved the remarkable feat of stopping light in carefully controlled laboratory conditions, a profound question emerges. Could the universe itself, through its own natural processes and extreme environments, ever bring light to a halt? This question takes us on a journey through some of the most exotic and extreme phenomena in the cosmos. From the event horizons of black holes to the expanding fabric of space-time itself. To explore this possibility, we must venture far beyond the comfortable confines of Earth-based laboratories and consider environments where the fundamental forces of nature operate at their most extreme limits. The universe contains regions where gravity is so intense that it warps space-time beyond recognition, where matter is compressed to densities that defy imagination, and where the very structure of space and time becomes distorted in ways that challenge our deepest understanding of physics. The most obvious place to begin this investigation is near black holes, those cosmic monsters where gravity becomes so strong that nothing, not even light, can escape once it crosses a critical boundary known as the event horizon. Black holes represent the ultimate victory of gravity over all other forces, creating regions of space-time so severely curved that the normal rules of physics break down in spectacular fashion. From the perspective of a distant observer watching light approach a black hole, something extraordinary and seemingly impossible occurs. As light falls toward the event horizon, it appears to slow down dramatically, its frequency shifting toward the red end of the spectrum as gravitational time dilation takes effect. The light appears to become dimmer and redder, eventually fading from view as it approaches the point of no return. To the distant observer, the light seems to freeze at the event horizon, never quite crossing over into the black hole's interior. Time dilation effects become so extreme near the horizon that what should be brief moments for the infalling light stretch into hours, days, years, and eventually into infinity from the external perspective. The light appears to be suspended in time, caught in an eternal moment at the threshold of the black hole. However, this apparent stopping of light is fundamentally different from the quantum mechanical processes we have explored in laboratory settings. The light is not actually stopped in any local sense. From the perspective of someone falling with the light toward the black hole, time continues to flow normally, and the light continues to propagate at its usual speed. The apparent freezing is entirely due to the extreme time dilation effects experienced by the external observer. This distinction is crucial for understanding the difference between gravitational time dilation and true light stopping. In the laboratory experiments with electromagnetically induced transparency, light is genuinely brought to rest through quantum mechanical interactions with atoms. Near black holes, light continues to move at the speed of light locally, but the extreme curvature of space-time creates the illusion of stopped light when viewed from a distance. Nevertheless, black holes do provide natural environments where light can be trapped and manipulated in ways that parallel some aspects of laboratory light, stopping experiments. The photon sphere, located at 1.5 times the Schwarzschild radius of a black hole, represents a region where light can orbit the black hole indefinitely. Photons following precise circular trajectories at this distance can circle the black hole forever, neither falling in nor escaping to infinity. These orbiting photons are not stopped in the sense of having zero velocity, but they are trapped in a kind of gravitational storage system. Like the quantum information stored in atomic media, these photons remain in a suspended state, preserving their energy and information while being held captive by the curvature of space-time itself. Even more exotic are the theoretical possibilities that emerge near rotating black holes known as Kerr black holes. The rotation of these massive objects drags space-time itself along, creating a region called the ergosphere, where the very fabric of space and time is twisted and distorted. Within the ergosphere, strange effects occur that seem to violate our normal understanding of causality and information flow. Some theoretical calculations suggest that under extremely specific conditions, near rotating black holes, light could potentially be trapped in complex orbital patterns that effectively halt its progress toward any particular destination. These trapped photons would continue to move locally at the speed of light, but their trajectories would become so convoluted by the twisted space-time geometry that they make no net progress through space. However, these scenarios remain highly speculative and would require black holes with properties that may not exist in nature. The extreme precision required for such gravitational light trapping makes it unlikely to occur spontaneously in realistic astrophysical environments, though it represents a fascinating theoretical possibility that continues to be studied by relativistic physicists. Moving beyond black holes, we encounter another arena where the universe might naturally manipulate light in extraordinary ways: the expanding universe itself. The discovery that the universe is not only expanding but accelerating in its expansion has revealed new possibilities for how cosmic scale phenomena might affect the propagation of light across vast distances. During the epoch of cosmic inflation, believed to have occurred in the first fraction of a second after the Big Bang, space itself expanded faster than the speed of light. This expansion created situations where light emitted from one region of space could never reach another region, even given infinite time, because the space between them was expanding faster than light could traverse it. In effect, cosmic inflation created natural event horizons in the expanding universe, boundaries beyond which information and causal influences cannot propagate. Light emitted beyond these cosmic horizons becomes trapped not by gravity, as in the case of black holes, but by the expansion of space itself. This light continues to propagate locally at the speed of light, but the expansion of the universe carries it away from its intended destination faster than it can approach. This cosmic trapping of light shares some conceptual similarities with the laboratory stopping of light, in that information becomes isolated and unable to propagate to distant observers. However, the physical mechanisms are completely different, involving the dynamics of space-time expansion rather than quantum mechanical interactions with matter. Current observations suggest that our universe continues to undergo accelerated expansion driven by dark energy, a mysterious component that makes up roughly 68% of the total energy density of the universe. If this acceleration continues indefinitely, it will eventually create situations where even nearby galaxies become causally disconnected, with light unable to travel between them due to the intervening expansion of space. In the far future, if dark energy continues to dominate cosmic evolution, the observable universe will gradually shrink as more and more distant regions disappear beyond the cosmic horizon. Light that is currently traveling toward us from distant galaxies will eventually be carried away by cosmic expansion, effectively trapped in the expanding space between galaxies and unable to reach any particular destination. This scenario, sometimes called the Big Rip, represents a cosmic scale example of how the universe's own dynamics can interfere with light propagation. While not identical to laboratory light stopping, it demonstrates that natural processes can indeed isolate light and prevent it from completing its intended journey through space. Another fascinating natural phenomenon that affects light propagation occurs in the vicinity of neutron stars, the ultra-dense remnants of massive stars that have undergone supernova explosions. These objects pack more mass than the Sun into spheres only about 20 kilometers in diameter, creating gravitational fields so intense that they approach the limits of what matter can withstand before collapsing into black holes. The extreme magnetic fields generated by rotating neutron stars, known as pulsars, can reach strengths of trillions of times stronger than Earth's magnetic field. These intense magnetic environments create conditions where the normal propagation of electromagnetic radiation becomes severely modified, with different polarizations of light following different paths through the magnetized space around the neutron star. In the most extreme cases, theoretical calculations suggest that the magnetic fields near magnetars, the most highly magnetized neutron stars known, could become strong enough to affect the vacuum properties of space itself. Quantum electrodynamics predicts that sufficiently strong magnetic fields can cause the vacuum to exhibit birefringence, splitting light beams according to their polarization, and potentially creating conditions where certain polarizations of light cannot propagate efficiently. While these effects do not constitute true stopping of light in the sense achieved in laboratory experiments, they represent natural examples of how extreme environments can dramatically modify the behavior of electromagnetic radiation. The universe provides magnetic field strengths and geometric configurations that far exceed anything achievable in terrestrial laboratories, potentially enabling forms of light manipulation that remain beyond current experimental capabilities. The search for natural light-stopping phenomena has also led astronomers to investigate gravitational lensing effects, where the curvature of space-time caused by massive objects acts like a lens, bending and focusing light from distant sources. In some cases, gravitational lensing can create multiple images of the same distant object, with light taking different paths around the lensing mass and arriving at different times. Extreme gravitational lensing events can create situations where light appears to be delayed for months or years as it follows longer paths around massive galaxy clusters or other gravitational lenses. While this does not constitute stopping light in a fundamental sense, it does demonstrate how natural gravitational phenomena can store and delay light over cosmological timescales. Recent theoretical work has explored whether sufficiently complex gravitational environments might create closed time-like curves or other exotic space-time geometries that could trap light indefinitely. These scenarios typically involve multiple black holes or other massive objects arranged in precise configurations that create stable orbital patterns for photons. However, most of these theoretical constructions require such specific and unlikely arrangements of matter that they are considered unphysical or unstable against small perturbations. The universe, despite its vast scale and diverse environments, appears to lack the fine-tuned conditions necessary to create natural analogues of laboratory light-stopping experiments. One of the most intriguing possibilities for natural light stopping involves hypothetical exotic matter with negative energy density. General relativity permits the existence of such matter in principle, and it could potentially create gravitational effects that oppose normal attraction, leading to repulsive gravity and other strange phenomena. Some theoretical models suggest that exotic matter could be arranged to create stable configurations that trap light without the extreme curvature associated with black holes. These configurations might act as natural optical cavities, holding light in suspended animation through gravitational effects rather than quantum mechanical interactions. However, exotic matter with the required properties has never been observed in nature, and many physicists believe that quantum effects or other fundamental principles may prohibit its existence in the forms necessary for gravitational light trapping. The cosmic censorship hypothesis proposed by Roger Penrose suggests that nature conspires to prevent the formation of naked singularities and other pathological space-time geometries that might enable such exotic phenomena. The study of cosmic ray propagation has also revealed interesting examples of how natural processes can affect high-energy electromagnetic radiation over vast distances. Cosmic rays, which include high-energy photons as well as charged particles, can interact with the cosmic microwave background radiation and other photon fields that permeate space. These interactions can lead to energy losses and trajectory modifications that effectively limit how far the highest energy photons can travel through the universe. While not constituting light stopping in a strict sense, these cosmic ray cutoff effects demonstrate how the universe's own radiation fields can interfere with photon propagation over cosmic scales. Recent discoveries in high-energy astrophysics have revealed gamma-ray bursts and other phenomena that produce photons with energies far exceeding anything achievable in terrestrial laboratories. These extreme photons probe regimes of quantum electrodynamics, where vacuum polarization and other quantum effects become important, potentially revealing new physics that could affect photon propagation in ways we do not yet understand. Some theoretical proposals suggest that the granular structure of space-time itself, predicted by certain theories of quantum gravity, might affect photon propagation over cosmological distances. If space and time are discrete rather than continuous at the smaller scales, this could lead to dispersion effects that accumulate over cosmic distances and potentially interfere with long-distance light propagation. However, current observations of distant gamma-ray bursts and other high-energy phenomena show no evidence for such quantum gravity effects, suggesting that if they exist, they are much smaller than naive estimates would suggest. The universe appears to preserve the smooth propagation of light, even over the largest observable scales. The question of whether the universe can naturally stop light also connects to fundamental questions about the nature of information and its role in cosmic evolution. If information is truly fundamental to the structure of reality, as some physicists propose, then the universe's apparent inability to naturally stop light might reflect deep principles about information conservation and the flow of causality through space-time. The laboratory achievements in stopping light represent a triumph of human understanding and technological capability, allowing us to manipulate quantum systems in ways that nature apparently does not achieve spontaneously. This suggests that there may be fundamental barriers preventing the natural occurrence of true light stopping, barriers that can only be overcome through the precise engineering of quantum mechanical systems. As our understanding of exotic astrophysical environments continues to advance, and as we develop more sophisticated theories of quantum gravity and fundamental physics, we may discover new natural phenomena that approach or even achieve the stopping of light through purely natural processes. The universe has repeatedly surprised us with its ability to create conditions far more extreme than we initially imagined possible. However, current evidence suggests that while the universe can dramatically modify light propagation through gravitational effects, magnetic fields, and cosmic expansion, it does not naturally achieve the quantum mechanical light stopping that has been demonstrated in terrestrial laboratories. This distinction highlights the unique achievement represented by human scientific and technological progress in understanding and controlling the fundamental constituents of reality. We began this journey with a question that seemed to violate the fundamental order of the universe. Can light, the fastest thing in existence, be brought to a complete stop? This question challenged everything we thought we knew about the nature of speed, motion, and the cosmic limits that govern reality. Through our exploration, we have discovered that the answer is not only yes, but that this achievement opens profound new windows into the deepest mysteries of existence itself. The story of frozen light is ultimately a story about the power of human curiosity and ingenuity to transcend apparent limitations and discover new possibilities hidden within the laws of nature. When Lena Howe first slowed light to 17 meters per second in 1999, she was not merely demonstrating a clever experimental trick. She was revealing that our understanding of light, motion, and time was far more limited than we had imagined. The journey from that first dramatic slowing to the complete stopping of light represents one of the most remarkable achievements in the history of experimental physics. It required the development of technologies that push the boundaries of what is possible with current scientific instruments, from laser cooling systems that approach absolute zero to quantum control techniques that manipulate individual atomic states with extraordinary precision. But the significance of stopped light extends far beyond the technical achievements required to demonstrate it. These experiments have forced us to reconsider fundamental questions about the nature of information, time, and reality itself. When light is frozen in an atomic medium, we are not simply storing electromagnetic energy, we are preserving quantum information in a state that exists outside the normal flow of time, creating a bridge between the moving and stationary worlds that reveals new connections between space, time, and information. The quantum mechanical nature of light stopping has illuminated the deep relationship between light and matter that underlies all of quantum mechanics. The ability to transfer quantum information seamlessly between photons and atoms demonstrates that the distinction between light and matter is not as fundamental as our everyday experience might suggest. At the quantum level, these different forms of existence are simply different ways of encoding and processing information about the state of the universe. This realization has profound implications for our understanding of information itself. The stopped light experiments suggest that information may be more fundamental than the particular physical systems that carry it. The fact that the complete quantum state of a light pulse can be transferred to atoms, stored for extended periods, and then retrieved with high fidelity indicates that information has a reality that transcends any specific material substrate. This insight connects the stopped light research to some of the deepest questions in theoretical physics about the role of information in the structure of reality. Some physicists argue that information is the most fundamental constituent of the universe, more basic than matter, energy, or even space-time itself. From this perspective, the universe is essentially an information processing system, and matter and energy are simply different ways of encoding and manipulating information. The stopped light experiments provide concrete support for this information-theoretic view of reality. They demonstrate that information can exist independently of its physical carrier and can be manipulated in ways that seem to transcend the normal constraints of space and time. When quantum information is stored in atomic media, it exists in a kind of temporal suspension that suggests information may have properties that are not bound by the usual rules that govern matter and energy. The technological implications of this understanding are only beginning to be explored. The ability to store and manipulate quantum information with the precision demonstrated in stopped light experiments could revolutionize computing, communication, and sensing technologies in ways that are difficult to imagine. Quantum computers based on optical memory systems could solve problems that are impossible for classical computers, while quantum communication networks could provide unprecedented security for sensitive information. But perhaps even more significant are the fundamental insights that stopped light research is providing into the nature of time itself. The ability to pause quantum evolution and then resume it without any loss of information challenges our basic assumptions about temporal flow and suggests that time may be far more flexible and controllable than we previously believed. When light is stopped, the quantum information it carries exists in a state where time effectively stands still. From the perspective of the stored information, no time passes during the storage period, yet the information emerges unchanged when it is released. This suggests that time is not the universal, flowing entity that our everyday experience suggests, but rather something that can be manipulated and controlled through precise understanding of quantum mechanical principles. This temporal flexibility revealed by stopped light experiments connects to some of the most profound questions in physics about the nature of causality, free will, and the relationship between past and future. If time can be paused for quantum systems without violating the fundamental structure of causality, this suggests that the universe may have a kind of temporal flexibility that allows for more complex relationships between cause and effect than traditional physics would predict. The exploration of natural environments where light might be stopped or dramatically slowed has revealed the extraordinary creativity of the universe in creating extreme conditions that push the boundaries of known physics. From the event horizons of black holes to the expanding fabric of space-time itself, the cosmos provides laboratories for testing the limits of our understanding that far exceed anything we can create on Earth. Yet remarkably, none of these natural phenomena appear to achieve true light stopping in the sense demonstrated in terrestrial laboratories. The universe can slow light, trap it, delay it, and manipulate it in countless ways. but the precise quantum mechanical control required to bring light to a complete halt while preserving its information content appears to require the kind of sophisticated engineering that only conscious intelligence can provide. This distinction highlights the unique achievement represented by human scientific progress. Through careful study of quantum mechanics and atomic physics, researchers have learned to control nature at a level of precision that apparently exceeds what nature achieves spontaneously. This suggests that consciousness and intelligence may play a special role in the universe, capable of discovering and implementing possibilities that would not emerge through purely natural processes. The philosophical implications of this realization extend far beyond physics into fundamental questions about the nature of mind, consciousness, and the relationship between intelligent beings and the physical universe. If intelligence can achieve forms of control over nature that do not occur spontaneously, this suggests that consciousness may be more than just an emergent property of complex matter. It may be a fundamental feature of reality that allows for new forms of order and organization that transcend the constraints that apply to purely physical systems. The stopped light experiments also demonstrate the profound interconnectedness of apparently separate areas of physics. Quantum mechanics, electromagnetism, atomic physics, thermodynamics, and relativity all contribute essential insights to understanding how light can be stopped and what this achievement means for our understanding of reality. This interconnectedness suggests that the universe may be far more unified than our specialized scientific disciplines might suggest. As research into stopped light and quantum temporal control continues to advance, we can expect even more surprising discoveries about the fundamental nature of space, time, information, and consciousness. The techniques developed for stopping light are already being applied to other quantum systems, revealing new possibilities for controlling and manipulating quantum states that could lead to technologies we can barely imagine today. The quantum internet, quantum computers capable of solving currently impossible problems, sensors that can detect gravitational waves from the Big Bang, and communication systems that are perfectly secure against any form of eavesdropping all represent natural extensions of the principles discovered through stopped light research. But even these remarkable applications may pale in comparison to discoveries we have not yet imagined. The story of frozen light is also a testament to the power of basic scientific research to transform our understanding of reality and create new technological possibilities. The ability to stop light emerged from fundamental investigations into quantum mechanics and atomic physics, research that was initially motivated by pure curiosity about how nature works at its most fundamental level. This pattern, where basic research leads to transformative applications, has repeated throughout the history of science. Quantum mechanics itself emerged from seemingly abstract investigations into the nature of light and atomic structure, yet it now underlies virtually all modern technology, from computers to lasers to medical imaging systems. Similarly, Einstein's theories of relativity grew out of fundamental questions about the nature of space and time. Yet they now enable the global positioning system and countless other practical applications. The stopped light research continues this tradition by demonstrating that even the most fundamental aspects of reality, such as the speed of light and the flow of time, may be more flexible and controllable than we previously imagined. This flexibility opens up possibilities for future technologies and scientific discoveries that could transform human civilization in ways we are only beginning to understand. The ability to freeze light also serves as a powerful metaphor for the human capacity to transcend apparent limitations through understanding and ingenuity. Just as our ancestors learned to harness fire, domesticate plants and animals, and eventually travel beyond the Earth itself, we are now learning to control the fundamental constituents of reality at the quantum level. This progression from basic survival to cosmic exploration to quantum manipulation represents an extraordinary expansion of human capability and understanding. Each step has required not just technological innovation, but fundamental advances in our understanding of how reality works and what is possible within the laws of nature. The stopped light experiments represent a particularly dramatic example of this progression because they involve controlling something that had been considered absolutely fundamental and unchangeable. The speed of light was thought to be one of the ultimate constants of nature, as fixed and unchangeable as the laws of mathematics themselves. Yet, through careful study and sophisticated experimental techniques, researchers have learned to bring even this cosmic constant under human control. This achievement suggests that many other aspects of reality that we currently consider fixed and unchangeable may actually be malleable under the right conditions. The fundamental constants of physics, the structure of space-time, the nature of consciousness itself may all prove to be more flexible and controllable than we currently imagine. As we look toward the future, the lessons learned from stopping light will undoubtedly inspire new investigations into the most fundamental aspects of reality. The techniques developed for quantum temporal control may lead to new forms of artificial intelligence that process information according to fundamentally different principles than biological systems. They may enable new forms of space exploration that transcend current limitations on travel time and communication delays. They may even provide new insights into the nature of life and consciousness that could transform our understanding of what it means to be human. But perhaps most importantly, the story of frozen light reminds us that reality is far stranger, more wonderful, and more full of possibilities than our everyday experience suggests. In a universe where light can be stopped, where quantum information can exist outside of time, where consciousness can control the fundamental forces of nature through understanding and technology, almost anything may be possible. We think of light as motion, as the ultimate expression of speed and change in the universe. But in the hands of physicists armed with quantum mechanics and sophisticated experimental techniques, even light can be paused, controlled, and manipulated like any other tool. To freeze light is not to break the universe's rules, but to learn how deeply those rules connect time, matter, information, and consciousness in ways we are only beginning to understand. The frozen light experiments represent just the beginning of humanity's exploration into quantum temporal control and the fundamental nature of information and time. As we continue to push the boundaries of what is possible, we may discover that the universe is far more responsive to conscious intention and understanding than we ever dared to imagine. In learning to stop the fastest thing in the universe, we may have taken the first step toward mastering time itself.